Someone is praying for you. Someone is praying for you. So when it seems you're all alone and your heart will break in two.
Let's look at Liouville's formula for Wronskian. But in the previous example, we realized that we knew the solutions of the function before we were able to compute the Wronskian of these functions. What about if we don't know the solution? Is it possible to compute the Wronskian of these functions? And that is what we want to take a look at. So let's take a second order differential equation, y prime prime plus p y prime as ky equal to 0. And since a second order, let's assume that y1 and y2 are solutions. If they are solutions, then we can substitute them into this function. It has to hold. That means y1 double prime plus py1 prime plus ky1 should be equal to 0, and y2 double prime plus py2 prime plus ky2 is also equal to 0. That means these are solutions and they are Wronskian. y1, y2 will be given by y1, y2, y1 prime, y2 prime, and that is equal to y1, y2 prime minus y1 prime, y2. That's what we have. Now, let's play around this a little bit. Let me call this one equation 1. If I differentiate the Wronskian of this function, then I'm going to use a product rule to differentiate these two functions. So I'm going to have y1, y2 prime prime plus y1 prime, y2 prime. That is for this one alone. Minus, then here too we have y1 prime prime, y2 minus y1 prime, y2 prime. So that is a derivative what we have here. If you open up the bracket, you're going to have y1, y2 double prime plus y1 prime, y2 prime minus y1 double prime, y2 minus y1 prime plus y1 prime, y2 prime. Okay, so when you differentiate the Wronskian, this one's supposed to, there you're supposed to get y1 prime, and then because we are using product rule, so we hold this and differentiate, we get y1 double prime, y2, then minus y1 prime. This was y1 prime plus here, plus here, so y1 prime and y2 prime. So if you open out the bracket, you're going to have this minus this. So you can see that this and this will go away. And we are left with y1, y2 double prime minus y1 double prime, y2. Now, if you check these two functions here, let me call this one A and B. Okay, so from these functions, if you make the highest derivative the subject from A, so from A, you can say that y prime prime will be equal to p y prime 1 plus p y prime 1, that's negative, minus ky 1. And from the B, you can see that the y2, this is y1, the y2 double prime is going to also go to negative p y2 prime minus ky 2. So what we want to do, we want to substitute the y1 and the y1 double prime, y2 double prime into the y2 double prime and the y1 double prime here. So the Wronskian, the derivative of the Wronskian here is now going to be y1 multiplied by y2 double prime, which is this negative p y2 prime minus ko y2 minus y2 multiplied by y1 double prime. Y1 double prime is negative p y1 prime minus ko y1. So if you open up this bracket, you're going to get negative p y1 y2 prime minus ko y1 y2 plus p y1 prime y2 plus ko y1 y2. When you do that, you realize that this and this will go off. So we'll be left with w prime of x to be equal to factorizing negative p out. You are left with y1 y2 prime minus y1 prime y2. And you can check here. The Wronskian of this function is y1 y2 prime minus y1 prime y2, which is this. So we can replace the whole of this here by this Wronskian, this one. So we can write this one as negative p times the Wronskian of x. So we have now realized that our Wronskian of x is negative p. The derivative of the Wronskian is negative p times the Wronskian. So if you want to solve this to compute the Wronskian, then we can separate the variable. So we can say w prime over w is equals to p. Don't forget w prime into w dx. So you're going to have p dx negative. So if you integrate both sides, you're going to get ln of w equals the integral of negative p dx. So w becomes e raised to the power negative the integral of p dx. And that becomes the Wronskian. Now if you compare this one to the second order ordinary differential equation, y prime prime plus py prime plus ky equal to 0. It simply means that in order to compute the Wronskian, you need to find your p. And then use this formula to find the Wronskian. And this is what you call the Liouville's formula for finding the Wronskian of a differential equation. So for example, if you are given y double prime plus sine x times y prime plus 3y equal to 0, you have to compute the Wronskian. We need to identify our p of x, which is what? Sine x. So the Wronskian of this function is simply e raised to the power negative the integral of sine x dx. If you integrate sine x, you get negative cos x. You are going to get e raised to the power negative of negative cos x. And this is going to give us e raised to the power cos x. So it means the Wronskian of this function is e raised to the power cos x. That means if you find the solutions, the independent solution of these functions, and you compute their Wronskian, this is what you are going to get. So this brings us to what we call the fundamental set of solutions. And this is simple. We are saying that if the functions y1 to yn are independent solutions of any differential equation, then those functions form what we call the fundamental set of solutions of that function. So for example, y1 equals to cos x and y2 equals sin x are the independent solution of this function. Therefore, y1 and y2 are the fundamental set of solutions because the two functions are linearly independent. Thank you for watching.